Hello friends, IBM is here with another episode of Learning Physics. Note that we have already introduced solutions to multiple choice questions, AS Physics 9702. I am hoping that you are preparing for your May-June series, and for those doing full A-levels, you must be now preparing, you must have accomplished paper 4 and paper 5. If you are new to this channel, consider going into the video description. You download the past paper questions which have been solved in the videos that have been uploaded on this website, on this site, on this YouTube channel. So we are dealing with multiple choice questions, and we have already finished atomic structure and particle physics. So today I would like to take you to errors and uncertainties. So let's go to errors and uncertainties. Errors and uncertainties. So let's go to errors and uncertainties. Okay, so this is the document. This is the document, and I'll start straight away. Errors and uncertainties. This is going to be unit 2. Number 1, in an experiment to determine the acceleration of free fall g, the time t taken for the ball to fall through distance s is measured. The percentage uncertainty in the measurement of s is 2%. The percentage uncertainty in the measurement of t is 3%. The value of g is determined using that equation. What is the percentage uncertainty in the calculated value of g? So because of division and the square, we just add up the percentage uncertainties. So the percentage uncertainty in G is going to be percentage uncertainty in S plus twice percentage uncertainty in T. We ignore the coefficient in front of S because we are dealing with the percentage uncertainties. So this is going to be in S it is 2% plus in T, which is going to be 2 times 3, which gives us 8. So our answer is C. A spring is suspended from a fixed point and a force is applied. The position of a pointer attached to the bottom of the spring against a vertical rule is recorded. Before the force is applied, the position of the pointer is 222, 225, and after the force is applied, the position is 250. The extension of the spring is determined. What is the percentage uncertainty in the extension? So we first get the uncertainty in the extension. We get the extension first. That will be 250 minus 225. So this is going to be 25 millimeters as the extension. But then the uncertainty in E is going to be the sum of the two absolute uncertainties. So this will be 2 millimeters plus 2 millimeters. That means the absolute uncertainty in E is going to be 4 millimeters. Then as a percentage uncertainty in E is going to be 4 divided by 25 times 100. So I think 4 times 100 divided by 25 gives us 4 times 100 divided by 25 gives us 16. So the answer is 16. A digital meter is used to measure the current in an electric circuit. The reading on the meter fluctuates. Since the readings fluctuate, we shall look for the smallest reading and the highest possible reading. Then we subtract them and we see the range of the uncertainty, then divide by 2 to get the average uncertainty. So the readings on the meter have an accuracy of plus or minus 1%. That means the minimum is going to be minus. Of course, the maximum will be plus. Let's first get the mean value. The average value of current, average value of I is going to be 3.04 plus 3.08 divided by 2. and this gives you 3.06 amperes. That's the average current. Then we can get I minimum. The minimum value of current we expect on the meter, considering this accuracy, is going to be the smallest value, which is 3.04, minus the uncertainty in this value, which is going to be 1 over 100 times 3.04. This gives us the minimum value of current. So this is going to be 3.04 minus 0.0304, which gives us 3.0, that is 3.0096 amperes. That is the smallest value we expect. Then the maximum value we expect, because the highest is 3.08, but if we consider the uncertainty, for maximum, of course, we add. So this is going to be 3.08 plus. The uncertainty is 3.08, which will be 1 over 100 times 3.08. And this will give us 3.08 plus 0.0308, which gives us 3.1108. So that is the highest value we can obtain. So if I want the absolute uncertainty in I, I'll just get the difference in this maximum and minimum, then I divide by 2. The same way we do in paper 5 analysis. So this will be 3.1108 minus 3.0096, and I divide this by 2. So that one minus 3.0096 divided by 2, which gives us 0.0506. To one significant figure, it is 0.05. Therefore, our answer is going to be, the current is going to be 3.06 plus or minus 0.05, which makes the answer to be C. A man of mass 75.2 kilograms uses a set of weighing scales to measure his mass 3 times. He obtains the following readings. First attempt 80.2, second attempt 80.1, third attempt 80.2. Which statement describes the precision and accuracy of the weighing scales? So not precise to 0.1 kilograms and accurate to 0.1 kilograms. They said which statement describes the precision and accuracy. Here it is saying not precisely, but they are precise. Precise to 0.1 kilograms, which is true, and accurate to 0.1 kilograms. Accurate to 0.1 kilograms, that is not true. It is not accurate to 0.1 kilograms, because we are seeing the man of the mass is 75.2 kilograms, so it is not accurate. Precise to 0.1 kilograms, which is true, but not accurate to 0.1 kilograms. That is true, so the answer is D. The precision is good, but the results, the average of these results does not give us 75.2, so it is not accurate. The value of the acceleration of free fall on Earth is given by that. Which statement is correct? We know that the correct value is 9.81 meters per second squared. So they are saying plus or minus. When I subtract plus, I get 98 is minus, and 10.12 is plus. Which statement is correct? The value is accurate but not precise. The value is both precise and accurate. Of course, the average should give us the average value should be 9.8, and we are seeing when we subtract plus 2, we get 98. When we add plus 2, we get 12. The value is both precise and accurate. Plus 2 is a very big difference, a very big range, so this one is not true. the value is neither precise and nor accurate. That value is actually accurate because it is very close to 9.81 meters per second. So this is not true. The value is precise but not accurate. The precision is poor because +2 and -2, that gives a range of 4 meters per second. The range is very big, so the value is not precise. Therefore, our answer is going to be A. The value is accurate because the average is close to 9.8, but not precise because the range between +2 and -2 is very large, so not precise. Which statement about systematic error is not correct? A systematic error can be caused by using an incorrectly calibrated instrument. A systematic error, they are saying not. A systematic error can be caused by using an incorrectly calibrated instrument. I think that is correct. One particular type of systematic error can affect all the measurements by the same amount. That is also correct. The effect of a systematic error can be reduced by repeating and averaging the measurements. That is not correct. This one, repeating and averaging the measurements, only improves a random error. So the answer is most likely C. Zero error is a type of a systematic error. That is correct. A micrometer screw gauge is used to measure the diameter of a small uniform steel sphere. The measurement of the diameter is 5 millimeters plus or minus 0.01 millimeters. What is the percentage uncertainty in the calculated volume of the sphere using these values? So we are using a micrometer screw gauge to measure the diameter of a sphere, and we know that the volume of a sphere is equal to 4/3 pi r squared, r cubed. So where there is r, because r is diameter over 2, so the volume is going to be 4/3 pi. Where there is r, I'll put diameter over 2, but this is raised to power 3. In other words, this is going to be 4 pi d cubed divided by 3 times 2 power 3, which is 8. So 8 cancels, remaining with the 2, that is pi d cubed over 6. So what is the percentage uncertainty in the calculated volume of the sphere? So the percentage uncertainty is just going to depend on d, and d is going to be cubed. So percentage uncertainty in V is going to be equal to 3 times the percentage uncertainty in D, which is going to be 3 times D, which is 0.0, the uncertainty in D, which is 0.01, divided by the true value, which is 5.00. Then we shall multiply this by 100. So that is 3 times 0.01 divided by 5, then times 100, which gives us 0.6. So this is going to be 0.6%. So the answer is C. Four possible sources of error in a series of measurements are listed down here. 1. An analogometer whose scale is read from different angles. A meter which always measures 5% too high. That is systematic. Of course, different angles, that is random. A meter which always measures 5% too high, that is systematic. A meter with a needle that is not frictionless, so the needle sometimes makes it random. A meter with a zero error, that is systematic. So the question is, which errors are random and which errors are systematic? So we now know that 1 and 3 are random, and we know that 2 and 4 are systematic. So the answer is B. A student measures the time t for one complete oscillation of a pendulum of length L. Here, her results are shown in the table here. Okay, she uses the formula t is equal to pi root L over G to calculate G. What is the best estimate of the percentage uncertainty in the value of G? So note that this is the same as 2 pi into brackets L over G power a half. So there's a power of a half. So we shall ignore the pi, 2 pi, because we shall be dealing with the percentage of fraction uncertainties. Therefore, we shall say the fraction uncertainty in t, which will be delta t over t, should be equal to a half into brackets fraction in L, which is delta L over L, plus fraction in, we want in G, sorry. We want in G, so I make G the subject. Let me make G the subject. This will waste a lot of time because we want uncertainty in G, not in T, since in T it was given. Okay, so making G the subject, this will be T squared equaling to 4 pi squared L over G, which means that G is going to be 4 pi squared L divided by T squared. So that is G. So it means a fractional in G should be equal to fractional in L plus twice, because of the power on T, twice fractional in T. When I multiply both sides by 100, it will be percentage. So percentage in G is equal to, in L, we have 0.01, I mean 001, divided by 0.420 plus in T, which is 2 times 0.1 divided by 1.3, but I will multiply this by 100 to make it a percentage. So I have 0.001 divided by 0.420 plus, open another bracket, 0.2 divided by 1.3. So that is the answer, times 100, which gives us 15.6. That is approximately 16%. So the answer is going to be D. After measuring the width of a shelf to be 305 millimeters, it is found that the graduations on the ruler used are 1.0% further apart than they should be. That is a wrong calibration. Which type of measurement error is this, and what is the true width of the shelf? Of course, wrong calibration is a systematic error. So we ignore A and B. They are saying what type of measurement error is this, and what is the true width of the shelf? After measuring the width of the shelf to be 3005, it is found that the graduations on the ruler used are 1.0% further apart. They are 1.0% further apart. That means the true width is most likely going to be greater than the width that has been measured there. Therefore, this is going to be the answer is going to be D, because the gradations on the ruler used are 1.0% further apart than they should be. That means the measurement obtained there, which is 305, is smaller than the true width. Therefore, the true width is supposed to be greater than 305, which gives us 308 as the true width. The value above 305 is actually 308. A student measures the current and the PD for a resistor in a circuit, as shown here. The measurements are used to calculate the resistance of the resistor. What is the percentage uncertainty in the calculated resistance? So we know that R is equal to V over I. So the percentage uncertainty in R is going to be the percentage in V plus the percentage in I. So this is going to be percentage in V is going to be 0.1 divided by 500 times 100 plus percentage in I, which is 0.01 divided by 50. So I'll multiply this by 100 to make it percentage. So 0.1 divided by 500 plus 0.01 divided by 50. Sorry. 0.1 divided by 500 plus 0.01 divided by 50 times 100, which gives us 0.04%, making the answer to be D. 0.04%. A micrometer screw gauge is used to measure the diameter of a wire. The reading on the micrometer with the jaws closed is negative 0.05 plus or minus 0.02. The reading with the wire in position between the two jaws is 1.03 plus or minus 0.02 millimeters. What is the diameter of the wire? So we are seeing that when the reading on the micrometer with the jaws closed is this, is the first one. And the reading with the wire in position between the jaws is given as that. So what is the diameter of the wire? So it means in the first case, when there is no wire, there is a negative zero error. So when there is a wire, the value is positive 1.03. That means this value here is actually less than the actual value by negative 0.05. So it means the true reading, the diameter is going to be 1.03 minus negative 0.05, which means the diameter is going to be 1.08. So it means we ignore the first one and this one here. Then how about the uncertainty in the reading? Of course, the uncertainty simply accumulates. Therefore, the uncertainty in the diameter is going to be 0.02 plus 0.02. Since to remove the error we subtracted, the uncertainty cannot be subtracted. So this just accumulates to 0.04, which makes the answer to be D. The uncertainty accumulates the true reading because without the wire, there's a negative zero error. Then with the wire, we get plus 1.03. It means this value is less than the true value by 0.05. So we just add it there. A student takes readings of the volume of a liquid using three different pieces of measuring equipment X, Y, and Z. The true value of the volume of the liquid, the true value of the volume of the liquid is V. The student's results are shown here. The student results are shown there. So we notice if the true value is V, it means this one is accurate, but there's a wide range, poor precision. Precision not good. Here you see that the peak is very narrow, precision is good, but the average is not the volume V, so accuracy is poor. Here we see that the peak is narrow, precision is good, but the peak is just coinciding with the V, so the accuracy is also good. So let's see the questions. How many pieces of equipment are precise and how many are accurate? So precise, we have Y and Z. Those are two. Number of precise pieces, we have C and D. Then accurate. Accurate, we have only Z. So accurate, we have 1. So the answer becomes C. Answer, no. This was also accurate, so the answer is not C. There were two pieces which were accurate. So the answer is D. The first one is accurate but not precise. Precise, not accurate. Precise and accurate. So precision there are 2, accurate there are also 2. Okay, the diameter of a circular disc is measured as plus or minus 7.0 plus or minus 0.1. What is the area of the disk and the absolute uncertainty in the area? It is a circular disk. If it is a circular disk, most probably it has what is the area of the disk and the absolute uncertainty in the area? So we know that area is equal to pi r squared, which is going to be pi d squared over 4. That is the area. So the uncertainty in the area is only going to depend on the uncertainty in D. The uncertainty in the area is only depending on the uncertainty in D. So, what is the area of the disk? So area is going to be pi times, the units are not changing, so D is going to be 7 squared divided by 4. So the area is going to be pi times 7 squared divided by 4. So that is 38.5. Automatically here there is only one, okay, 38.5. We have this one and this one. So we ignore C and D in millimeters squared. Then let's check the uncertainty to be very sure of which of the two is the most appropriate here. So for uncertainty in D, remember we shall take the last part. We don't use the one of the radius. So uncertainty in the area divided by the area is going to be equal to twice uncertainty in D divided by D. We ignore all the coefficients and the constants. Ignore all the coefficients and the constants. So this means the absolute uncertainty in the area is going to be 2 times that one in the diameter, which is 0.1. Divided by 7.0 times the area itself, which is 38.5. So we check on the calculator. So the answer was that one. So I will say times 2 times 0.1 divided by 7, which makes it 1.00. As a whole number, one significant figure, this is approximately 1. So it is going to be a whole number. That means the area should also be quoted as a whole number, making the answer to be B. So the answer there is B, plus or minus 1 and 38. The power P dissipated in a resistor, R of resistance R is calculated using the expression P is equal to V squared. P is equal to V squared over R. We are familiar with that expression. What is the percentage uncertainty in P? Where V is the potential difference, across the resistor. The percentage uncertainty in V is 5% and in R is 2%. What is the percentage uncertainty in P? So percentage uncertainty in P is simply going to be twice percentage in V plus percentage in R. So this means I'll have 2 times in V, which is 5, plus in R, which is 2. And that gives us 12%. So the answer is D. A micrometer is used to measure the 28.5 nanometer width of a plastic ruler. The micrometer reads to the nearest 0.01 millimeters. What is the correct way to record this reading? So they have changed the reading into meters. Let's first see the correct conversion. So this is 28.50 divided by 1000. 28 0.5 divided by 1000. So this is the correct reading is 0.0285. That is the correct reading. To change the uncertainty in meters, is going to be 0.01 divided by 1000, which is 1. The uncertainty is 1 times 10 power negative 5. That is the uncertainty. So number 1, here the number of decimal places is not the same as that of the uncertainty, so that one we ignore it. Even the conversion of the uncertainty is not correct. So these two, if we expand, this will be 0.00001. 1, 2, 3, 4, 5. So these two are wrong. Then we have 3 decimal places here, 3 decimal places there. To 3 decimal places, the uncertainty is going to be 0.001 times 10 power. I've moved 1, 2 steps. So that is times 10 power negative 2, not negative 3, which makes D to be wrong also. So that means the correct answer is going to be C. Okay. The sides of a wooden block are measured with the calipers. The lengths of the sides are measured as 20 millimeters, 40 millimeters, and 10 millimeters. The calipers can measure with an absolute uncertainty of plus or minus 0.1 millimeters. What is the percentage uncertainty in the calculated volume? So we want the percentage in the calculated volume. So we know that volume is going to be side or length times width times the height. Because of multiplication, we just sum up the percentage or absolute uncertainties. So the percentage in volume will be the percentage in L plus the percentage in the width plus the percentage in the height. This will be equal to, for L. Remember, the calipers measures with an absolute uncertainty of plus or minus 0.1. So in L, it is going to be 0.1 divided by L, which is maybe 40. In the width, it will be 0.1 divided by the width, which is maybe 10. And the height, it is 0.1 divided by the height, which is 20. I'm just ignoring the decimal places there. Then I'll multiply this one by 100 to make it percentage. So we have 0.1 divided by 40 plus 0.1 divided by 10 plus 0.1 divided by 20 what have I done here? 0.1 divided by 40 plus 0.1 divided by 10 plus 0.1 divided by 20, then times 100. So that is the uncertainty I'm obtaining here is 1.8%. So this is 1.8%, which makes the answer to be B. What could reduce systematic errors? Averaging large number of measurements, that one reduces random. Careful calibration, I think calibration is systematic. Reducing the sample size does nothing. Repeating measurements, that does nothing. So the answer is B, careful calibration. Because there are two common systematic errors, the zero error and wrong calibration. Zero error and wrong calibration. Wrong calibration, they are the most common systematic errors we interact with. Wrong calibration. So if there is careful calibration, then the systematic error is reduced. The power loss in a resistor is calculated using that formula. Power is that the percentage uncertainty and the potential difference is 3% and the resistance is 2%. What is the percentage uncertainty in P? So we have already seen a similar question. Percentage uncertainty in P will be equal to, because there is a power on V, so it will be twice percentage in V plus percentage in R. So this will be 2 times 3 plus 2, which makes it 6 plus 2, which is 8%. So the answer there is C. 4 students measure a time interval that is known to be 1.734. That is the true value. The measurement recorded by each student is shown. Which measurement is the most accurate? Which measurement is the most accurate? So it is known to be 1.73. So 1 second has a very large uncertainty. 1.83 is above. 1.6004 is below. So it means the most accurate value is this, because when you round off, you can get 1.7. That is obvious. The speed shown on a car's speedometer is proportional to the rate of rotation of the tires. The variation of the diameter of the tire as wears introduces an error in the speed shown on the speedometer. A car has new tires of diameter 600 millimeters. The speedometer is accurately calibrated for this diameter. The tires wear as shown, with 6 millimeters of material being removed from the outer surface. 6 millimeters are being removed from the outer surface. So what is the error in the speed shown on the speedometer after this wear has taken place? What is the speed shown on the speedometer after this wear has taken place? So going back, they are saying 6 millimeters. There are 6 millimeters of wear. The speedometer is accurately calibrated for this diameter. A car has new tires of diameter 600 millimeters. 600 millimeters. Then the speedometer is accurately calibrated for this diameter. The tire wears as shown, with 6 millimeters of material being removed. 6 millimeters of material is being removed. So it means the diameter has actually reduced. So what is the error in the speed shown on the speedometer after this wear has taken place? So if we consider the cross-sectional area, we know that area is equal to pi d squared over 4. So it means the uncertainty in the area is going to depend on twice the uncertainty in the diameter. So if 6 millimeters of material wears out, then it means the uncertainty in the speed. What is the error in the speed shown on the speedometer? Somewhere they must have mentioned that the speed shown on the car speedometer is proportional to the rate of rotation of the tires. The variation of the diameter of the tire as it wears introduces. The variation in the diameter as it wears introduces an error, and the variation is now going to be 6 meters. So the uncertainty here is going to be twice times 6 divided by 600, then times 100. So this gives us 2 times, because of the power on the diameter, the cross-sectional area is directly proportional to diameter squared. So this is going to be 2 times 6 divided by 600, then times 100, which gives us 2%. So the speed shown is too high by 2%. So because the diameter reduces, that means the speed is going to be too high by 2%. Somebody may be asking, why is the speed shown not too low? The speed shown on the car's speedometer is proportional to the rate of rotation of the tires. The variation of the diameter of the tire as it wears introduces an error in the speed shown in the speedometer. So if the tires, a layer is removed from the tires and means the circumference is very small, it means the rate of rotation of the tires increases. That's why I'm saying the speed shown is too high by 2%. A student wishes to determine the density rho of lead. She measures the mass and diameter of a small sphere of lead. Mass is given, diameter is given. What is the best estimate of the percentage uncertainty in her calculated value of rho? So he wishes to measure the diameter. We have mass and diameter. Density is equal to mass over volume. And we are dealing with a sphere. The volume of a sphere is 4 over 3 pi r cubed, which is 4 over 3 pi, and where there is r, I put d over 2 cubed, which gives us 8 cancels, so it becomes pi d cubed over 6. So we want what is the best estimate of the percentage uncertainty in the calculated value of rho. So density is going to be 6m divided by pi d cubed. Percentage uncertainty in density will be percentage in m plus 3 times percentage in d, which will be equal to, in m we shall have 0.005 divided by 0.506 plus 3 times 0.02 divided by 2.20. Then we multiply this by 100. So we have open brackets 0.005 divided by 0.506 plus open another bracket, I will say 0.06 divided by 2.2 times 100. So we are getting the percentage here as 3.7. So this is going to be 3.7%, making the answer to be D. Two quantities P and Q are directly proportional to each other. Experimental results are taken and plotted in a graph of Q and P, of Q against P. Which graph shows there were random errors in the measurements of P and Q? Remember, random errors makes values to scatter around the true value or around the line of best fit. So here we are seeing line of best fit. Here there is no random error because all values are along the line, the curve of best fit. No random errors here. Here we are seeing only one value above, so we can't say there is a random error. Maybe that is an anomaly or poor plotting. But here we see values scattering above and below the point, the line of best fit. That means the answer is going to be C. There were random errors. The values scatter around the line of best fit. A man of 75.2 kilograms uses a set of weighing scales. To measure his mass 3 times, he obtains the following readings. We have seen a similar question. So we expect that if there is no random, if there is no systematic error, if the values are accurate, the average should be 75.2. But these values cannot give us that average, so they are not accurate. But there is a precision, they are close to each other, so precision is relatively good. So where we see accurate, that means that is wrong. Where we see accurate, it means that is wrong. They are not accurate. But precise. B is saying not precise to 0.1, they are precise. So this one is wrong. They are precise but not accurate, making the answer to be D. The micrometer screw gauge is used to measure the diameter of a small uniform steel sphere. The micrometer reading is 5 millimeters plus or minus 0.01. What will be the percentage uncertainty in a calculation of the volume of the sphere using these values? We want percentage uncertainty, volume. We have already seen that the volume of a sphere is 4 over 3 pi r cubed, which becomes 4 over 3 pi into d over 2, but is cubed, which becomes pi d cubed over 6. So we want the percentage uncertainty in calculating of the volume. So percentage in volume is going to be 3 times percentage in d, which is 0.01 over 5 times 3, then times 100. So this is 0.01 times 3 divided by 5 times 100, which gives us 0.6%. A micrometer is used to measure diameters of two cylinders. Diameter of the first cylinder, diameter of the second cylinder, they are given here. The difference in the diameters is calculated. Let's check the difference. What is the uncertainty in the difference? We don't need the difference anyway. Because we are subtracting, we are getting a difference. To find the difference in the diameter, the uncertainty is simply add up. So the absolute uncertainty in the diameter is going to be 0.02 plus 0.03. We don't subtract uncertainties when we get a difference in two measured values using the same instrument. So the answer here is going to be D. A measurement is taken correctly but with a ruler. A measurement is taken correctly but with a ruler at a significantly high temperature. At a significantly high temperature than that at which the ruler was calibrated. The higher temperature causes the ruler to expand. What describes the effect on the measurement caused by the higher temperature and how the measurement may be improved? So the measurement will be subject to a random error. The measurement can be made more accurate by taking the average of several repeated measurements. That's not a random error. If the temperature has increased and it has made the ruler to expand, it means every time we use the ruler, this has affected the calibration. So every time we use the ruler, it means we are using a wrongly calibrated instrument because the divisions have moved further apart. The measurement will be subject to a random error. It is not a random error. It is a systematic error. The measurement will be subject to a systematic error. Yes. The measurement can be made more accurate by taking average. We don't improve a systematic error by taking average, so that's not true. The measurement will be subject to a systematic error, which is true. The measurement can be made more precise by taking the average of several repeated measurements. This is made more precise, not accurate, but made more precise. So we can improve precision by taking average, but we can't improve accuracy by taking average. So the answer is going to be D. Readings are made of the current I for different voltages V across a fixed resistor. The results are plotted on a graph to show the variation of I with V, as shown here. What is the best description of the errors in the readings? Best description. So when we draw a line through these values, I think it is a straight line. So it is a straight line. So we don't expect a random error. All values are on the straight line, so there is no random error. Both systematic and random error, there is no random error. It is only systematic. So the answer is systematic only because there is a y-intercept. When v is 0, I is not 0. So there is a systematic error. There is no random error because all values are on the line of best fit. Two liquid in glass thermometers in a well-mixed liquid are individually observed by 10 different students. All agree that one thermometer reads 21 degrees Celsius. One thermometer reads 21 degrees Celsius. and the other thermometer reads 23 degrees Celsius. What is the possible explanation for the difference? Of course, this is now the liquid is not all at the same temperature. Two liquid thermometers in a well mixed liquid. It is well mixed, so this one is not true. The liquid should be at the same temperature. The readings are not precise. That cannot explain the difference in the two thermometers. All agree that one thermometer reads 21 and the other reads 23. There must have been a systematic error in one of the thermometers. There is a random error affecting the readings. That one does not does not come here. There is a systematic error affecting the readings. There could be a systematic error in one of the thermometers. That is very true. That's why two thermometers are placed in the same well-mixed liquid, but they are reading two different values. The diameter of a spherical golf ball is measured with calipers and found to be 4.11 plus or minus 0.01 centimeters. The volume of a sphere is V equals to 1 over 6 pi d cubed, where this is the diameter. What is the volume of the golf ball? What is the volume of the golf ball? So the diameter is found to be that. So volume is going to be 1 over 6 pi. Diameter is, the answers are in centimeters cubed, so I'll just say 4.11 cubed. So 4.11 cubed, then times pi, divide by 6. So we have 36.35 centimeters cubed. That is the volume. Then we need to find the uncertainty. So absolute uncertainty in volume is going to be 3 times absolute in d over d, then times the volume. So this is going to be 3 times the absolute uncertainty in d, 0.03, 0.1, divide by d, which is 4.11, times the value of volume, which we have got 36.35. So this gives us 0.265, which is 0.3. So this is 0.3. And this makes the answer to be D. The answer should be D. So if this is 1 decimal place, we round off this to also 1 decimal place. A student measures the length L and the period T of oscillations of a simple pendulum. He then uses the equation to calculate the acceleration of free fall G. His measurements are shown in the figure. What is the percentage uncertainty in his calculated value of G? So we make G the subject. So G is going to be equal to 4 pi squared L divided by T squared. So we want the percentage uncertainty in G. So percentage in G, we ignore the 4 pi squared. So it will be percentage in L plus twice percentage in T. So this will be L. Percentage in L is 0.2 divided by 87.3 times 100 plus 2. In T, it is 0.05 over 1.9. Then we multiply this by 100. So 0.2 divided by 87.3 plus 2 times 0.05, that is 0.1. 0.1 divided by 1.9, then times 100. So this is giving us 5.5%. So the answer is C. A steel ball is dropped and falls through a vertical height h. The time t taken to fall is measured using light gates. The results are given in the table. The acceleration of free fall g is calculated using the equation h is equal to half gt squared. What is the percentage uncertainty in the value of g? So when I make g the subject, I obtain that g is equal to twice h divided by t squared. So I want the percentage uncertainty. Percentage in g is equal to percentage in h. We ignore the coefficient 2 plus twice percentage in t. So percentage in h is 0.01 divided by 4.05 plus 2 times 0.02 divided by 0.91. As a percentage, this is times 100%. So we have 0.01 divided by 4.05 plus 0.01 plus divided by 4.05 plus, that is 0.04 divided by 0.91, then times 100. So that is 4.6%. So this is 4.6%. So the answer is B. A person calculates the potential difference across a wire by using the measurements shown. Which measured quantity has the greatest contribution to the percentage uncertainty in the calculated potential difference? A person calculates the potential difference across a wire by using the measurements shown. Which measured quantity has the greatest contribution to the percentage uncertainty in the calculated potential difference? So we have a current in the wire, the value is 5.0, the percentage uncertainty is 0.5. Then we have diameter in the wire, the value is 0.8, and the absolute uncertainty is plus or minus 0.1. Then the length of the wire is 150, the percentage uncertainty is the uncertainty is plus or minus 5. Then resistivity of the metal in the wire, 1.6 times 10 power negative 8, and 0.2 times 10 power negative 8. So although there could be a missing question here. The person calculated the potential difference across a wire by using the measurements shown. So cross-sectional area of the wire is equal to pi d squared over 4. So it means the diameter is going to be, the uncertainty in the diameter is going to be multiplied by 2. And then the length, that one is fine. So which measured quantity has the greatest contribution to the percentage uncertainty in the calculated potential difference? So I think there is a formula missing here. There's a formula missing for the PD. There's a formula missing for the PD, but then the answer here will depend on the power. It will depend on the formula and the power of each of these quantities. Assuming that a potential difference is equal to current times resistance, and resistance is equal to rho L over cross-section area, which is going to be 4 rho L over pi d squared. It means V is going to be equal to I times resistance, which is 4 rho L over pi d squared. So we can check using that formula and see. So the uncertainty due to the current is going to be 0.5 divided by the value, which is 5.0. That is the contribution of I. The uncertainty caused by resistivity is going to be 0.2 times 10 power negative 8 divided by 1.6 times 10 power negative 8. That is the contribution for the resistivity. The contribution for L, the length of the wire, will be 5 divided by 150. Then the contribution for D will be twice times the diameter, which is the uncertainty in diameter, which is 0.1 divided by 0.8. Let's check which of these fractions is bigger. So 0.5 divided by 5, that is 0.1. Let me change the color. Let me change the color here so that I write the values on top. So this one is 0.1. Then 0.2 divided by 1.6. So this is 0.125. Then we have 5 divided by 150. That is 0.3 recurring. This is 0.03 recurring. Then we have 2 times 0.1 divided by 0.8, which is 0.25. 0.25. So this one is contributing more. The diameter will be contributing more, so the answer there will be B. Okay. The sides of a cube are measured with calipers. The measured length of each side is 30 plus or minus 0.1. The measurements are used to calculate the volume of the cube. The cube has all sides equal. So it means the volume is going to be side cubed, or L cubed. What is the percentage uncertainty and calculated value of the volume? So percentage uncertainty in volume will be 3 times percentage in the side. So this will be 3 times 0.1 over 30. Then I multiply this by 100 to make it percentage. So that is 3 times 0.1 times 100 divided by 30, which gives us a 1%. A student measures the current through a resistor and a PD across it. There is a 4% uncertainty in the current reading and a 1% uncertainty in the PD reading. The student calculates the resistance of the resistor. We know the resistance is V over I. What is the percentage uncertainty in the calculated resistance? So percentage in R is going to be percentage in V plus percentage in I. So percentage in V is 1, percentage in I is 4, which makes our answer to be 5%. A student applies a PDV of 4.0 plus or minus 0.1 volts across a resistor of resistance R of 10.0 plus or minus 0.3 ohms for a time t of 50 plus or minus 1 second. The student calculates the energy dissipated using the equation below. E is equal to V squared T over R and gets 80 joules. What is the absolute uncertainty in the calculated energy value? Absolute uncertainty. So this is the formula. So absolute uncertainty in energy is going to be equal to, this is over energy, is going to be twice absolute in V over V plus absolute in T over T plus absolute in R over R. So we shall multiply both sides by E. So let's just substitute in the calculator. For So this is going to be 2 times V, 0.1 over 4.0 plus T is 1 over 50 plus the R is 0.3 over 10. Then we multiply this by E, which is 80. to get the absolute in E. So this will be 0.2 divided by 4 plus 1 divided by 50 plus 0.3 divided by 10 times 80, which gives us 8%. So the uncertainty is going to be 8%. I mean 8 joules, not 8%. In an experiment to determine the Young modulus E of the material of a wire, the measurements taken are shown here. So they have the mass, we have original length, we have diameter of the wire, we have extension. They have given us a formula there, where G is the acceleration of free fall. E has been calculated to be 1.61 times 10 power 10 meters. How should the calculated value of E and its uncertainty be expressed? Let's first calculate the uncertainty in E. So absolute uncertainty is going to be, we ignore M, ignore 4 and pi. So it will be uncertainty in M divided by M plus G is a constant, so we shall also ignore G and M. So we have uncertainty in L over L plus twice uncertainty in D over D plus uncertainty in the extension over E. Then I will multiply this by the value of E which was calculated. So this will be 0.002 divided by 2.300 plus L 0.005 divided by 2.864 plus 2 times 0.01 divided by 0.82 plus 0.2 divided by 7.6, and this is going to be multiplied by E, which was calculated to be 1.61 times 10 power 10 to get the absolute in E. So let's check. Open brackets 0.002 divided by 2.3 plus open another bracket 0.005 divided by 2.864 plus open another bracket 0.02 divided by 0.82 plus open another bracket 0.2 divided by 7 point, that is 7.6, then times 1.61 exponent 10, so that is 8.58, 8.58 times 10 power, so 1 2 3 4 5 6 7 8 times 10 power 8. So that is going to be the uncertainty. Remember, the power of the uncertainty, the power of 10 of the uncertainty should be the same as the power of 10 of the true value. So I am going to move 2 steps to the left. So 2 steps to the left, it is going to become 0.0858 times 10 power 10, which is the same as 0.09 times 10 power 10. So these are 2 decimal places. So the answer is going to be D. So the answer there is D. 1.61 plus or minus 0.09. Students take readings of the volume of a liquid using 3 different pieces of measuring instruments, X, Y, and Z. We have seen a similar question. The true value of the volume of the liquid is V. The students' results are shown here. How many pieces of equipment are precise and how many are accurate? So here the accuracy is good because the average is V, but there's a wide range between the values, so the precision is poor. Here the precision is good because the peak is very narrow, but the accuracy is poor because the average is not is somewhere here, it's not V. Here the peak is the average, and the peak is very sharp, so the precision is narrow, is good. The accuracy, the average is actually V, so the accuracy is good. So How many pieces of equipment are precise? Precise, we have 2. And then accurate, accurate we also have 2. So the answer there will be D, 2, 2. The width of a table is measured as 50.3 plus or minus 0.1 centimeters. Its length is measured as 1.4 plus or minus 0.01. What is the area of the table and its absolute uncertainty? So area is the length times the width. So the area is going to be 50.3. Of course, this is over 100 to change it to meters, times 1.40. This one is in meters, so there's no need of changing. So 50.3 exponent negative 2 times 1.4. So that is 0.7042. That is the area in meters squared. Then absolute uncertainty. So absolute uncertainty in the area is going to be absolute in L over L plus absolute in the width over W. Then we multiply this by the area. So this will be in L. Here I don't need to convert. 0.01, 1.4 plus 0.1, 50.3. Then I multiply this by L. I mean by the area, which is 0.7042. So I have 0.01 divided by 1.4 plus 0.1 divided by 50.3 times 0.7042. So that is 6.4 times 10 power negative 3, which is 0.00643. To one significant figure, it is 0.006. Those are 3 decimal places. So the answer is going to be B. 3 decimal places here, 3 decimal places there. A student attempts to find the density rho of aluminium by taking measurements of a rectangular sheet. It is rectangular. The mass is given, length, width, and thickness have been given. He uses the equation rho is equal to m over WLT to calculate the density. What is the calculated value of density with its uncertainty? So let's first find the density. So the density is going to be, the answers are in grams per centimeters cubed, so I don't convert anything. The density is going to be 5.16 divided by W, 10, then L is 100, and then T is 0.2. Because it is in millimeters, I'll just say times 10 power negative 1, because 1 centimeter is equal to 10 millimeters. Or we divide 0.2 by 10. So we now find the answer here. So this is going to be 10 times 100 times 0.2 exponent negative 1. That is 20. So it is 5.16 divided by 20. This is in grams, this is in centimeters cubed. So 5.16 divided by the answer. So that is 0.258 grams. Okay, let's now find the absolute uncertainty. Absolute uncertainty in density is going to be absolute in M divided by M plus absolute in W divided by W plus the absolute in L divided by L plus the absolute in T divided by T. Then I multiply this by the density rho. So we substitute for M, 0.1 divided by 51.6 plus 0.1 divided by 10 plus L 0.1 divided by 100 plus T 0.01 divided by 0.2. Then times density, which is 0.258. So we open the bracket, 0.1 divided by 51.6 plus 0.1 divided by 10 plus 0.1 divided by 100 plus 0.01 divided by 0.2 times 0.258. So that is giving us 0.016, which is 0.02. Those are two decimal places, so we write the answer two decimal places. So the answer is going to be B. The answer here is going to be, is it two decimal places? Let me compute this again. So we have 0.1 divided by 51.6 plus 0.1 divided by 10 plus 0.1 divided by 100 plus 0.01 divided by 0.2, okay, times 0.258. So that is 0.002. So that is 0.02, which makes the answer to be B. Decimal places, that makes the answer to be B. Oh, no. 0.26 grams per centimeters cubed. Let me check this one. 2.6. One step, that is no, the answer is B. The answer there is B. It is not D. Okay, so this was grams per centimeters cubed, and here it is also grams per centimeters cubed. So the answer is going to be B. Okay. The current in a block of a semiconductor is 30 milliamperes when there is a potential difference of 10 volts across it. The dimensions of the block and the direction of the current in it are shown here. So this shaded part is the cross-section area. The electrical meters used are accurate to plus or minus 0.1 milliampere and plus or minus 0.1 volts. The dimensions of the block are accurate to plus or minus 0.2 millimeters. What is the resistivity of the semiconductor? So we know that resistance is equal to rho L over cross-section area. So we want the resistivity is going to be R times A divided by L. The dimensions of the block are accurate to plus or minus 0.2. Let's first find we have the PD across and we have the current. So it means the resistivity is going to be PD. Remember, R is equal to V over I. So this is going to be V times cross-sectional area over I times L. So V is the unit sign as not SI, so V is 10. Then I is 30 times 10 power negative 3. Cross-sectional area is going to be 15, area is 15 over 100 times 30 over 100. So area is going to be, so this is going to be 15 times 30 divided by 100 times 100. That is the area. Then divide by the length. So I will say times 1 over the length, which is just going to be this distance here. So that is going to be 15 times 10 power negative 3. No, this is in millimeters, so I add there 1 0. So this is 0 0. Okay, so let's press the calculator. So V is 10 divided by 30 exponent negative 3. 30 exponent negative 3. Then times 15 exponent negative 3 times 30 exponent negative 3. Then divide by 15 exponent negative 3, which gives us 10. So the resistivity is 10 ohm meters. So all of them are 10, so there is no need of verifying 10 again. What is important is now the uncertainty in resistivity. So they say the electrical meters use the actuate to this one and that one for the voltmeter. The dimensions of the block are actuate to plus or minus 0.2. So remember resistivity is going to be V, that is L times width, that is length times width. Okay. Then divide by I times the length which is through which the current is flowing. So this is going to be, this will imply that the absolute uncertainty in rho is going to be absolute in V over V plus absolute in L over L plus absolute in the W over W plus absolute in I over the current plus again absolute in L over L. Then I will multiply this one by the density. So we just substitute here. For V, it is 0.1 over 10. For the length L, okay, I'll just take it as 15. The uncertainty is 0. The uncertainty in the measurements is 0.2 divided by 15 plus what I'm calling the width could be the height, which is going to be 0.2 divided by 30. For the current, it is 0.1 milliamperes. So this is 0.1 divided by 30, again plus L, which is 0.2 divided by 15. Then I multiply this by rho, which is actually 10. 0.1 divided by 10 plus 0.2 divided by 15 plus 0.2 divided by 30 plus 0.1 divided by 30, then plus 0.2 divided by 15 times 10. So that is 0.46 recurring, which is 0.5. So this is 0.5. So this makes the answer to be C. The voltage is carefully measured with a high quality instrument and found to be 2.321 volts. Two students using two different methods conclude that the voltage is 2.33 and 2.344 volts respectively. Which statement is correct? 2.33 is less accurate and less precise than 2.344. Okay, that is not very correct. 2.33 volts is less accurate than and more precise than 2.344. That is also not true. It's not less accurate. It is actually more accurate than the other one. Then 2.33 is more accurate, which is true, and less precise than 2.33, which is true, because 2.344 has more decimal places than 2.33. So that means the instrument in the second part is more precise than the first one. So the answer is C. 2.33 volts is more accurate, which is true, and more precise than this one. This instrument, which measures to 2 decimal places, cannot give a more precise value than the one which measures to 3 decimal places. Or a method where you're recording to 2 decimal places cannot be more precise than one where you're recording to 3 decimal places. A double-slit interference experiment is used to determine the wavelength of light from a monochromatic source. The following measurements are used: slit separation A, fringe separation X, distance between slits and the screen D. What is the percentage uncertainty in the calculated wavelength? So we know that lambda is equal to AX divided by D for the double slit experiment. So percentage uncertainty in lambda will be percentage in A plus percentage in X plus percentage in D. So this gives us percentage in A will be 0.02 divided by 0.5 plus in X 0.1 divided by 1.7 plus in D 0.002 divided by 2.00. We shall multiply this by 100. So we have 0.02 divided by 0.5 plus 0.1 divided by 1.7 plus 0.002 divided by 2 times 100, which gives us 9.98, which is approximately 10%. That is 10%. So the answer is D. A spool has a piece of aluminium that it uses for radioactivity experiments. Its thickness is marked 3.2 millimeters. A student decides to check this value. He has vernier calipers which give measurements plus or minus to 0.1 millimeters and a micrometer screw gauge which measures to 0.01 millimeters. Which statement must be correct? The micrometer gives a more accurate measurement. The micrometer gives a more accurate measurement. It may not be giving a more accurate measurement, but the micrometer gives a more precise measurement because these values are showing that the reading of the micrometer is going to be more precise than that of the vernier caliper. All values could be accurate, but for the vernier caliper it could be more precise. 4 possible sources of errors in a series of measurements are listed. An analogometer whose scale is read from different angles, that is a random error. A meter which always measures 5% too high, that is systematic. A meter with a needle that is not frictionless, so the needle sometimes sticks, that is random. A metal with a zero error, that is systematic. Which errors are random and which errors are systematic? So we know that 1 and 3 are random, 2 and 4 are systematic. Quantity x has a fractional uncertainty of x. Quantity y has a fractional uncertainty of y. What is the fractional uncertainty in x over y squared? So fractional uncertainty in x over y squared is going to be fractional in x plus twice fractional in y, which is going to be fraction in x is x and fraction in y, so this will be plus twice fraction in y, which is small y. So the answer here is going to be C. When performing an experiment, a student should minimize the uncertainty of any measurement, in which case is the student reducing the systematic error in a measurement. Adjusting the voltmeter needle pointer to the zero position, this student is removing the zero error, so that is removing a systematic error. In which case is the student reducing the systematic error in a measurement, that is adjusting a voltmeter needle pointer to the zero position. Measuring the diameter of a wire at several points, that is random. Measuring the mass of 100 paper clips to determine the mass of one paper clip, that one does not deal with systematic. Timing 20 oscillations, that is still random, so the answer is A. A student determines the density or rho of steel by taking measurements from a steel wire. The mass is given 6.2 plus or minus 0.1. The length is given 25.0 plus or minus 0.1. The diameter is given 2.0 plus or minus 0.01. Uses that equation, what is the percentage uncertainty in his calculated value of density? We want percentage uncertainty, so percentage in rho is going to be percentage in m plus twice percentage in d plus percentage in L. So this will be percentage in m is going to be 0.1 divided by 6.2 times 100 plus percentage in d, which is 0.01 divided by 2 times 100 plus in L 0.1 divided by 25.0 times 100. So this will be times 100. So I'll open 0.1 divided by 6.2 plus 0.02 divided by 2 plus 0.1 divided by 25 times 100. So that is 3%. So this is 3.0%. So the answer here is D. The value for the acceleration of free fall on Earth is given by that expression 10 plus or minus 2 meters per second. Which statement is correct? The value is accurate but not precise. Of course, this value is accurate. The value is accurate. However, the precision is going to be the range. The highest value is 10 plus 2, which is equal to 12. The lowest is 10 minus 2, which is equal to 9, which is equal to 8. So the difference here is the range is going to be 4 meters per second. So this range is very large, so not accurate. The value is both precise and accurate. It is accurate, but the range is very large. The value is neither precise or accurate, it is accurate. The value is precise but not accurate. It is not precise. An experiment to determine atmospheric pressure uses that equation where P is this, G is given, H is given. What is the value of P with its actual uncertainty? So let's first calculate P as the units are SI, so we shall simply say pressure density 13600 times G 9.81 times H, which is 0.762. So 13600 times 9.81 times 0.762. So this is equal to 101,662. 101,662 as the pressure in pascals. Now we want the uncertainty in that pressure. So absolute uncertainty in P will be fraction in density over density plus fraction in G over G plus fraction in H over H. Then we multiply this by the pressure P. So for density, we have 100 divided by 13,600. For G, we have 0.02 divided by 9.81. For H, we have 0.005 divided by 0.762. And then we multiply by the pressure, 10,1662 pascals. So we check with our calculator, 100 divided by 13,600 plus 0.02 divided by 9.81 plus 0.005 divided by 0.762 times 101,662. That is 1621 pascals. So to one significant figure, I think this is going to be 2000 pascals, or 2 times 10 power 3 pascals. Now we can check this. So this is 1 2 3 4 1 2 3 4. Okay, but this is more than one significant figure to absolute. This is also more than one significant figure to absolute. Then we can check C. C is 1.6%. I don't think it is 1.6%. Then again times 10 power 5. This is wrong automatically. So the answer is going to be D. You can find out how why. If the power of this is 1.016662 times 10 power 5. We make this one to have power of 5, so we move 2 steps to the right, to the left. So that is 0.02 times 10 power 5. So these are 2 decimal places. This one should also be 2 decimal places, which makes it 1.02. So the answer is D. The strain energy W of a spring is determined from its spring constant K and extension X. The spring obeys Hooke's law. The value of W is calculated using the equation W is equal to half kx squared. The spring constant is 100 plus or minus 2 newtons per meter, and the extension is 0.05 plus or minus 0.02 meters. 0.002 meters. What is the percentage uncertainty in the calculated value of W? So the percentage in W is going to be equal to, we ignore the half, percentage in K plus twice percentage in X. So we just substitute. Percentage in K is going to be 2 over 100 times 100 plus 2 times X, 0.002 divided by 0.05. Then I'll multiply this by 100. Open brackets, 2 divided by 100 plus 0.00. I will just multiply to get it 4, divided by 0.05 times 100. And that gives us 10%. So the answer is B. That is 10%. A signal sheet of aluminium foil is folded twice to produce a stack of 4 sheets. The total thickness of the stack of sheets is measured to be 0.8 plus or minus 0.02. The measurement is made using a digital caliper with a zero error of negative 0.20. What is the percentage uncertainty in the calculated thickness of a single sheet? So first of all, the true value for the thickness, total thickness of the stack is that. So thickness is going to be 0.8 minus negative 0.2, which is going to be equal to 1.0 in millimeters. That is the thickness of all the four. Then for one thickness, what is the percentage uncertainty in the thickness of a single sheet? So for one it is going to be 1.0 divided by 4, which is a quarter, or 0.25 millimeters. That is the thickness of one. What is the percentage uncertainty? What is the percentage uncertainty in what is the percentage uncertainty in the thickness? So what is the percentage uncertainty in the thickness of a single sheet of paper? So for a single sheet of paper, of course, the thickness is going to be, or the absolute uncertainty in the thickness is going to be 0. That would be 0.02 plus 0.02. Sorry for that snap. So the absolute uncertainty here is going to be 0.04 millimeters. But remember the true value, the average, the value is 1.04 millimeters. That is the total uncertainty there. I mean the total value for the 4. So then this means as a percentage uncertainty in the thickness is going to be 0.04 over 1.0 times 100, which gives us 4%. Of course, the percentage uncertainty in the thickness is going to depend on the uncertainty in all the 4. So the absolute uncertainty in the measured value for all the 4 is 1 millimeter, and therefore the percentage uncertainty in the measured value of all the 4 is actually going to be 4%, which is going to be the same percentage uncertainty in the thickness of a single sheet of paper, because the instrument is being used just once. Therefore the answer here would be C. Okay, I feel very tired. In an experiment to determine the acceleration of free fall G of a ball bearing is held by an electromagnet. When the current to the electromagnet is switched off, a clock starts and the ball bearing falls. After falling a distance h, the ball bearing strikes a switch to stop the clock, which measures the time t of the fall. If systematic errors cause t and h to be measured incorrectly, which error must cause G to appear greater than 9.81? So here we are actually looking at if systematic errors cause T and H to be measured incorrectly, which error must cause G to appear greater than 9.81? So we know that G or H is going to be a half times GT squared, which means G is going to be twice H divided by T squared. So the question is saying which error must cause G to appear greater than 9.81. So you see that G is directly proportional to H. If there is a greater error in H, it means G is going to be higher. If there is a greater error in T, it means G is going to be smaller. So H measured as being smaller than it actually should be. That is not true. H measured as being smaller than it actually is, and T measured as being larger. That's not true. H measured as being larger than it actually is, and T measured as being larger. That's also not true. H is measured correctly. H is measured correctly, and T measured as being smaller. When T is small, of course, G is going to be greater than it actually is. So this will give a larger value of G. H measured as being large, they are directly proportional. T measured as being large, it reduces. So the answer is D, because G is going to be directly proportional to H, but inversely proportional to T, or to T squared. 4 different students use a ruler to measure the length of 15 centimeter pencil. Their measurements are recorded on 4 different charts. A. So which chart shows measurements that are precise but not accurate? Precise, they should be very close. So these ones are not precise, these ones are not precise, these ones are precise, and these ones are precise. So they are saying which chart shows measurements that are precise but not accurate. Remember, the true value is 15. These ones are precise, but they are very far from, their average is far from 15. These ones are precise, but you see their average is around 15. So the answer here is, they're saying precise but not accurate. So the answer is going to be B, precise but not accurate. These ones are precise but not close to 15. These ones are precise, but their average is 15. So the answer is B. In a simple electrical circuit, the current in a resistor is measured as 2.5 plus or minus 0.05 milliamperes. The resistor is marked as having a value of 4.7 plus or minus 2%. If these values were used to calculate the power dissipated in the resistor, what would be the percentage uncertainty in the value obtained? So power is equal to V squared. No, they gave us I and V. So power, I and R. So power is V squared over R. Power is equal to I squared times R. So it means the percentage uncertainty in the power is going to be twice percentage in I plus percentage in R, which makes it to be 2 times in I. In I, it will be 0.05 divided by 2.5 times 100 plus R, which is 2%. So this is percentage. So this is 2 times 0.05 divided by 2.5 plus, sorry, times 100 plus 2, which gives us 6. So the answer here is going to be 6%. A calibrated graph is shown for the ammeter, an ammeter whose scale is inaccurate. Scale is inaccurate. 2 readings taken on the meter at different times during an experiment are 0.13 milliamperes and 0.47 milliamperes. By how much did the current really increase between taking the 2 readings? So they said a calibration graph is shown for an ammeter whose scale is inaccurate. The scale is inaccurate. So this is the ammeter reading, and then this is the current. So two readings on the meter at different times during an experiment are 0.13, 0.1. The scale here is 0.1 divided by 5, which is 0.1 divided by 5, 0.02, 0.02. So 0.13 is somewhere here, which reads 0 point on the x-axis. The current is 0.1 0.214. Then 0.47, 0.42444647 is here. So 47, this is actually 0.444. So this is 0.44 minus 0.14, which gives us 0.30. By how much did the current really increase between taking the two readings? So that is 0.30. Four identical rods have a square cross-section. The rods are placed side by side and their total width is measured with the vernier calipers as shown. The measurement is 8.4 plus or minus 0.1. And the zero reading on the caliper is 0.0 plus or minus 0.1. What is the width of one rod? Of course, there are four. So that is 8.4 divided by 4. 8.4 divided by 4, that is 2.1 millimeters. Then what is very important is now the uncertainty. So the measurement is 8.4 plus or minus 0.1. And they are actually 1, 2, 3, 4. So the uncertainty in this measurement is actually going to be the same as, so this is going to be 0.1 plus 0.1, and since there are four, so this is the absolute uncertainty in the measurement. Let me call it, how should I call it, measurement. Okay, let me just call it a reading. An absolute uncertainty in the reading is going to be that for the total reading, since there are four, absolute in R is going to be a quarter of 0.1 plus 0.1, which is equal to 0.2 divided by 4, which is 0.05. So this is 0.05. So the uncertainty is 0.05, and these are two decimal places. So we shall divide this, we shall write two decimal places for the true values. A student measures the time t for one complete oscillation of a pendulum of length L. Her results are shown in the table. So she uses that formula to calculate the acceleration of free fall g. What is the best estimate of the percentage uncertainty in the value of g? So we make g the subject. So g is going to be equal to 4 pi squared L divided by t squared. So percentage in g is equal to, we ignore the 4 pi squared, so it is percentage in L plus twice percentage in t. So this is going to be 0.001 divided by 0.420 plus 2 times 0.1 divided by 1.3. Then I multiply this by 100. So open the brackets, 0.001 divided by 0.42 plus, open another bracket, 0.2 divided by 1.3 times 100. So that is 15.6, which is approximately 16%. So the answer there will be D. Which measurements are subject to systematic errors and random errors? Which measurements have high accuracy and low precision? High random error, that is low precision, and high systematic error, that is let me see. A high random error means low precision, and a high systematic error means lower accuracy. So this is low accuracy, low precision. High random error means low precision. Lower systematic error, that is lower systematic error. If the systematic error is lower, then the accuracy is high. So the answer is going to be B. Variables x and y are related by the equation y is equal to p minus qx, where p and q are constants. Values of x and y are measured experimentally. The results contain a systematic error. Which graph best represents these results? The results contain a systematic error. Which graph best represents these results? So A, they said y is equal to p minus qx. Y equals to p minus qx. The results contain a systematic error. The results contain a systematic error. So if y is equal to p minus qx, it means the gradient. On the y-axis, we have the gradient is equal to negative q, and the y-intercept should be p. The y-intercept should be p. So this one is below p. This one is p. This one is p. That is fine. This one is above p, so this is wrong. So we have this one and this one here. So since they have a systematic error, of course here this is showing that there's a random error. Values scatter around the line of best fit. And here, so the answer is going to be between B and D. B is showing that the gradient is, remember P and Q are constants. Values of x and y are measured experimentally. The results contain a systematic error. This one is showing a random error, so it means the answer is going to be D. Okay, so the results will be, the answer will be D. Lastly, an experiment. An experiment is carried out to measure the resistance of a wire. The current in the wire is 1.0 plus or minus 0.2, and the PD across the wire is 8 volts. What is the resistance? So R is equal to V over I, which will be, of course, all values are the same. So I'll just find the uncertainty and the resistance, which will be V 0.4 over 8 plus I, which is 0.2 over 1.0, then times 8. Find the uncertainty, because 8 is the R for all. So I will just say open brackets 0.4 divide by 8 plus open another bracket 0.2 divide by 1, then times 8. I didn't calculate 8 again because it's the same for all. So it means it's the resistance. So this gives us 2. Therefore, it means our answer to this is going to be D. The Young modulus of the material of a wire is to be found. The Young modulus is given by that expression. The wire is extended by a known force. The wire is extended by a known force, and the following measurements are made. Which measurement has the largest effect? Which measurement has the largest effect on the uncertainty in the value of the calculated Young modulus? So just check. If we try to find the uncertainty in the Young modulus, absolute uncertainty in E over E will be absolute in F over F plus absolute in L over L plus twice absolute in D over D plus absolute in X over X. We can check for F. For F, it will be 0.01 divided by 19.62, which is 5.1 times 10 power negative 4 plus for L 0.0202 divided by 2.043, which gives us 9.7 or 9.8 times 10 power negative 4. We can check for F. Now we have finished F. We can check for D. D is going to be 2 times 0.02 divided by 0.54, which is plus 0.0474 recurring. Then for X, we can check for X 0.2 divided by 5.2, which is 0.04. 0.04. So we see that D is contributing much. So the answer is going to be B. Okay, let part 1 stop there. We shall meet in part 2. All the best. If there is any mistake or any error, you have to bear with me because I am bound to make some mistakes. Nevertheless, I try my level best to avoid errors, but at least I hope you have learned something from this video. All the best. Bye bye.